Hi there. So today I'd like to talk to you about electromagnetic fields and forces and what relativity has to say about these things. So maybe before this class you've heard that electromagnetism was sort of unified and that electric and magnetic fields were the flip sides of the same coin. But you might not have had much experience with applying this knowledge because say you're given the force between 2 point charges, right? K, Q1, Q2 over R squared. Then that would be how you would calculate that force, and it seems like magnetic fields don't really enter into it. And so what does that even mean? Okay, so today we're going to explore and take you through a series of thought experiments that will hopefully make you understand a little bit better why electric and magnetic fields are really sort of the same thing. So to do that, I'm going to take you through a series of thought experiments. So here's the first one, all right? You've got two perspectives. The red is going to be the stationary observer, and blue is the moving observer. And blue moves to the right with a speed u as compared to red. So what's happening here is that blue in this case is a positive charge. And blue is moving to the right there through a uniform magnetic field that's pointing into the screen. That's why the X's with the circles in them, okay? Now the Lorentz force law states that F is equal to QU cross V in this situation. So this is a vector cross product between the charge times the velocity and then cross product with the magnetic field. That would result in an upward force on our blue positive charge here, okay, if you apply your right-hand rule. So we're going to remember throughout this lecture that charge, like mass, is invariant under transformations. So what happens is red sees a magnetic field that's into the screen and concludes that that magnetic field causes a magnetic force on blue, the moving charge. Now, let's put ourselves in the perspective of blue. According to blue, red's the one that's moving. Red's moving to the left with a speed u. Okay? Now, since blue knows that magnetic fields don't cause forces on stationary charges, but blue still sees an upward force on himself, he's going to conclude that there's no magnetic field there, right, causing a force. Well, there might be a magnetic field, but it's not changing anything for him because he's not moving. And since F is equal to QU cross B, if there's no U, then there can be no force on him, okay? So what he's going to say is, no, there's an electric field here because I'm a stationary charge, all right? I'm a stationary charge, so if I'm feeling a force, it has to be due to an electric field. Now we're going to use the prime to indicate from the perspective of the moving frame. Now, the force on a stationary charge in an electric field is QE. So what blue will see is a force, QE prime, acting on him, pushing him upwards. And now since both red and blue have to agree that there's a force, they have to agree that the magnitude of the force should be the same, then what we can conclude is that any upward force that blue sees in his frame has to be equal to the force seen by red in his frame. So here we have QE prime is equal to QU cross B. Or, canceling Q out of both sides of an equation, E prime is equal to U cross B. So this is our first example that if you change the reference frame, that you're sort of shifting perspective and calling a magnetic field in one frame an electric field in another frame. Flip sides of the same coin. Now, I want to point out that this did not require special or general relativity. This is pure old Galilean relativity here, and just saying that the physics has to be the same in both reference frames. In other words, the laws of physics have to apply equally to both frames, and that's what we've done here. Now, more generally, if there's both a magnetic field and an electric field according to red, as shown here, then there'd be a force from both the electric and the magnetic field, okay? And so what red would see in this case, for example, if there was an electric field pointing to the right and a magnetic field pointing in, then due to the electric field pointing to the right, blue would experience a force to the right, and due to the magnetic field into the screen here, blue would experience a force up, which means that the net force would have to be the sum of those to the right and up. And so you'd end up with a force QE plus QU cross V. And then from the perspective of blue, blue would still have to see that force up and to the right. However, blue would say that that was all due to an electric field because blue sees itself as stationary. And what that means is that if you set this QE prime equal to the perspective of red, then you would have QE prime is equal to QE plus QU cross B. You could cancel the Q's out, and you have E prime is equal to E plus U cross B. Yet again, good old Galilean relativity, and what you have is a shift showing that what was an electromagnetic field in one frame, an electric and a magnetic field that are perpendicular to one another, can become due to just an electric field from the perspective of the other frame. Okay, pretty cool, right? Let's now consider a new situation, okay? In this situation, you've got red and you've got blue, and they're both observing a positive point charge. Now, from the perspective of red, the charge is at rest. According to red, blue is moving to the right at a speed u. But what blue would see is a point charge moving to the left with speed u, and red moving to the left with speed u. So these are the two perspectives on the same situation. Now, let's say that at a position x that's some distance away from that point charge, red is going to observe an electric field. And that electric field is going to point away from that stationary point charge. We learned the equation in introductory physics. This equation for the electric field according to a point charge is 1 over 4 pi epsilon naught times q over r squared, where r is the distance away from the point charge to the point. And then r hat is just a vector that symbolizes a unit vector pointing radially away from that positive point charge. Now, that's what the electric field that red would observe. But what would blue see at that point, that same point, x? Well, blue agrees there's an electric field at x from the point charge. Charge is invariant and it's some distance away from that point charge. So sure, they would agree, and they would agree on what the electric field was. This is pure old Galilean relativity, remember. We're not getting into, speeds close to the speed of light yet. Now, since blue sees the charge as moving to the left, blue says that there's also going to be a magnetic field due to that moving point charge. Because remember, moving charges or currents cause magnetic fields. So according to blue, that magnetic field B prime would be created by this moving charge, and the magnitude of that would be mu naught over 4 pi q over r squared, and then minus u because it's going to the left, cross r hat. And that would give you the magnetic field created by that moving charge at that point x. Now we could rearrange this simple equation and then just put everything multiplying the point charge next to the r hat vector, all the constants next to the r hat vector. And then you have B prime is equal to minus u cross mu naught over 4 pi q over r squared r hat. Now we could rearrange this value and notice that this q over r squared 1 over 4 pi bit looks just like this electric field equation right here. And then we could just put it in terms of minus u cross epsilon naught mu naught times the electric field. Okay, just rearranging and solving for the constants. If you need a little help with the algebra, be sure and pause the video and make sure that you can recreate the steps that I've done right there in that equation. All right? So what we've seen here is that from the perspective of red, you just have an electric field. But from the perspective of blue, you have both an electric field and a magnetic field at that point x. So what we can say is that there is going to be a magnetic field from the perspective of blue. That magnetic field is going to be minus epsilon naught mu naught u cross E. And you can expand this argument and say that if there were a stationary field already there from the outside source, just like in the previous example, then it would still be there in the moving frame. So if you already had a stationary magnetic field present there, it would still be there in the moving frame, and then that extra magnetic field, due to the fact that the point charge is moving according to blue, would just add on to that. And so you'd end up with B prime is equal to B from the perspective of the stationary frame minus epsilon naught mu naught u cross E. And this is kind of akin to the previous situation where we had the equation for the electric field from the perspective of blue. E prime is equal to E plus U cross B. So these are transformation equations for stationary observers in the unprimed frame to moving observers in the primed frame. Okay, so you can see that what's an electric field or a magnetic field in one frame could be something else according to another frame. So what's the point? Electricity and magnetism here we can see, with just plain old Galilean relativity, aren't really separate entities. They're flip sides of the same coin. The laws of physics have to be the same in all inertial frames of reference. And that means that if you can change a magnetic field into an electric field just by changing your frame of reference, that it was always both. So this is why we call these forces electromagnetic forces and fields. So tomato, tomato, kind of. So to remind you, we don't need special or general relativity for any of this. So you might be saying, why is she even talking about this? Well, I do have a situation where special relativity does come into play, and it's kind of cool. So here we go on that. Here it is. Okay. Third situation. Here we have a stationary observer, and we see a point charge moving to the right at some speed u above a current carrying wire. Okay. Now, in this wire, a current is flowing because there's it's basically a typical metal. You have these ions in the metal, and then this free electron gas, which is moving around. Now, the free electrons here are moving to the right with a speed u that's equal to the speed of the test charge q naught moving to the right. Okay, so everything here is, in this perspective, is moving to the right. And then the positive ions are stationary, which is kind of what you'd expect in a typical metal. Now, in this case, the wire has no net charge. Like I said, it's a typical metal. So you have the same number of free electrons as you have ionic cores, so the net charge is 0. There are equal numbers of equally spaced positive ions and negative charges in this wire. All right? Hopefully that's clear. Now, according to the stationary observer, what is going to happen here? Well, because that test charge Q naught is moving, and because there's a magnetic field created by the current, then there's going to be a Lorentz force on that positive test charge Q naught. And that Lorentz force is going to be moving upwards. Okay? This is because there's a magnetic field created at the position of Q naught that's into the screen in this case. Right? Okay, so remember, current is defined as the motion of positive charges. So since here it's the negative charges that's moving, instead of the current pointing to the right as it is here in the screen, the current actually points left. Okay? Now you can take your right-hand rule. You point your thumb in the direction that the current's flowing, and you curl your fingers to indicate the direction that the magnetic field is going to curl around that wire. So at the top of the wire, the magnetic field points into the screen, and then it loops around the wire and comes out of the screen below the wire and makes circles around it. So the magnetic field from this current carrying wire is going to make circles around that wire, pointing into the screen above and out of the screen below. Now Q naught is above, and it's a positive charge. So if you apply your right-hand rule, Q, U cross B here, then the force due to that magnetic field on that moving charge will be upwards. All right? Now the magnetic field due to an infinite current carrying wire is equal to mu naught I over 2 pi r, where r is the distance radially away from the center of the wire to the test charge. All right? So the magnetic force magnitude here would be Q naught U times mu naught I over 2 pi r. All right? So that's what's going on there. Now, let's think about what would happen if, instead of the perspective from the stationary observer in red, which is kind of similar to what you might see in an introductory classical physics course, now you put yourself in the perspective of a moving observer, the blue observer here. Now, the blue observer is moving to the right along with that positive test charge, right, at the same speed and in the same direction. So, according to that blue observer, that positive test charge is at rest. Remember also that those negative charges were moving to the right at the same speed as the positive test charge. So now, according to the blue observer, those negative charges are at rest. That means, though, that the positive charges, according to the blue observer, are moving to the left. So both the blue and the red agree that there's a current in the wire. Okay, so they both agree that there's a current. But blue would say that it's the positive ones that are moving. Okay, they would also agree on the direction of the current. It's the negative charges moving to the right versus the positive charges moving to the left, but both of those would agree that the current vector would have to point left. Okay, and that's the way current vectors work. Thank you, Ben Franklin. Okay. Now, blue would agree that the current generates a magnetic field. However, the test charge Q naught is at rest. So blue would argue that there's no magnetic force on that test charge. However, they both have to still see a force. That has to be the same across the moving and the stationary reference frame. They both have to see the force. The charge Q naught is still going to be deflected upwards for both of them, and they both have to explain that. Now, blue would argue that the force has to come from an electric field because that charge is stationary. So here's the real conundrum. Since electric fields come from a net charge and not a current where the charges are balanced, right? You have to have a net charge according to Gauss's law in order to say that there's a force on a test charge at some distance. We argued that red saw no net charge on the wire, that there were equal numbers of equally spaced positive and negative charges in that wire. So where the heck does that net charge come from? Here's the answer. Blue actually sees length contraction in the spacing of those positive charges. Okay? Blue says, I'm at rest. Those positive charges are moving towards me outside of my reference frame. And so what they would see is the charges are closer together than they are according to red. If they're closer together, then that means that from the other perspective, the negative charges had to be further apart. Okay? So if the negative charges are further apart and the positive charges are closer together, then that means that blue sees an increased charge density. Okay? In other words, there's going to be a net positive charge per unit length according to blue. All right? We're going to call this linear charge density lambda. And lambda will be the net charge per unit length on that wire. Okay? This net linear charge density causes an electric field force that repels that positive test charge away from the wire, and that's the source of the force for blue. Okay? Crazy, but true. Now, I'll show you the proof of this in the lecture, but here's the answer. In the end, blue and red are going to agree that that charge Q naught, that little test charge, experiences a force upwards. Blue will say it's due to an electric field force on that stationary charge Q naught from the wire, and that that wire has a net charge. They'll both say there's a current in the wire, and they'll agree on the direction of current. Okay? However, blue says that that current, while it would create a magnetic field, the magnetic field cannot exert a force on a stationary charge. Red will say there's a current in the wire, but no net charge. And since Q naught's moving according to red, the magnetic field due to the current causes a force. They're both going to agree on the magnitude of that force, if not its source. Okay? And the magnitude of that force will be equal to mu naught times Q naught lambda u squared over 2 pi r, where mu naught's the permeability of free space, Q naught is the test charge, lambda is the linear charge density, u is the speed, and r is the distance radially away from the center of the wire to the test charge. So they're both going to agree on the magnitude of that force. That's the proof I'll present in class, but hopefully the conceptual basis of that has now been explained. Okay? So watch this as many times as you need to. Pause it when you need to. It's a tricky concept to grasp, but I hope that this introduces you to the idea that electric and magnetic forces are really flip sides of the same coin. That what might be an electric force from one reference frame is a magnetic force in the other, and vice versa. And so these forces are really united. And this was one of the ideas that led Einstein to develop the theory of relativity. See you in class.